Hello, my name is Robert Smith, and I'm with New River Community College's Academic Assistance, and today we are looking at the classification of bonds. In our previous video, I mentioned briefly covalent and ionic. We're also going to be looking at polar covalent, which occurs quite frequently. So let's get started. We're looking to classify these compounds, as either covalent, ionic, or polar covalent. Simple enough. Okay. So let's look at this. This is hydrogen bromide, which is just HBr. And if we were to draw the Lewis dot structure for this, we could see it as very simply, it would just be hydrogen. Hydrogen has one electron, and then bromine has 7. So hydrogen would have one bond to the bromine, and then bromine would have 1, 2, 3, 4, 5, 6 electrons around it. It's a fairly simple Lewis dot structure. Now, in doing this, we have to understand that electrons are flowing to the most electronegative species in the compound. So in this particular molecule, hydrogen bromide, bromine is significantly more electronegative than hydrogen. So you could feasibly draw a dipole moment here, if you desired. Basically saying that it's going from hydrogen to bromine, that you have a scenario in which the electrons are moving away from the hydrogen atom and toward the bromine atom. Even though they're connected, even though you do have that bond between hydrogen and bromine, that the electrons are tending toward bromine, because electrons are not stationary. They're moving around, they are in constant motion. So they're not just staying static around bromine or around hydrogen, but they're generally flowing toward bromine. And this resulted, this little dipole this little vector that I've drawn there at the bottom in red, that's indicating the flow of the electrons. And whenever you have these vectors and they don't balance out, that means that you have a polar covalent bond. Polar means to one side, to a pole. So in this case, hydrogen bromine is a polar covalent bond, the bond between hydrogen and bromine. Now, our next one is sodium chloride, NaCl. And if you remember back from chapter 2 or 3, you have sodium chloride is a metal and a nonmetal, so it's ionic. So this is relatively easy to identify. You're going to have, even if you were to write this out, that sodium has 1 valence electron and chlorine has 7, that's a total of 8, you would end up having Na plus and a Cl with 8 electrons surrounding it and a minus charge. So this is an ionic bond. The idea being that they're attracted to each other through its ionic charges, rather than there being what we would term a formal bond between sodium and chlorine. So we've got a polar covalent in hydrogen bromide. We've got a ionic in sodium chloride. So now let's take a look at our last example, which is the carbon-carbon bond in CH3, C3 edit. Carbon-carbon bond in C3H8. That's propane, if you don't know your molecule yet. So if we were to draw this out explicitly, including all the hydrogens and all the carbons, it would look in a very rudimentary way, because this is not including any of the angles or anything like that, but the molecule would look a little bit like this. And if you were to draw dipole moments between the little vectors between the hydrogen and the carbon, again, hydrogen is less electronegative than carbon, so electrons would be flowing to there. And this is accurate also in its drawing as in terms of a Lewis structure, because carbon has 4 valence electrons, hydrogen has 1. Each of them would be making a bond to the carbon. Each carbon has 4 bonds to it. Each bond counts as 2 electrons. 2 times 4 is 8, so each carbon has its octet satisfied. So if we were to look at all these little dipole moments, they're all kind of canceling each other out in their own sense. And that's important to recognize. As a molecule as a whole, propane is a nonpolar molecule. But we're asked specifically for the carbon-carbon bond between the carbons in the C3H8. So notice that I didn't put a dipole moment between them because carbon has the same electronegativity as the other carbon. It doesn't have, there's no change. They're all singly bonded to each other. There's just no difference in where the electrons want to flow toward. So while there is a dipole moment between the hydrogen and the carbon, they cancel each other out, and that makes this whole thing nonpolar, and there's nothing between the 2 carbons themselves. So this would just be a covalent bond. Not polar, just plain old covalent. So covalent bonds between carbon and carbon, polar covalent bonds between hydrogen and bromine, and ionic with sodium and chlorine.